Hi everyone. Let's take a look at some separable differential equations. So I'm going to do probably one of the ones that's asking you for a general solution, and then one or two of the ones that are asking you for a particular solution. And this particular solution thing, I mean, it comes up here, but it comes up a lot of other places in your review packet as well, because that is definitely a skill that we are like building so we can use it for other things. But let's maybe start with just number 5. I think number 5 looks adequately tricky. Okay. First of all, how do you know when to use separable differential equations? Definitely anytime. So I guess let me back up. A solution to a differential equation is an antiderivative. Okay. That's what we mean when we say find a solution. I mean find an antiderivative. Okay. You can't take an antiderivative of something if it's got multiple variables in it. Like I can't just come in here and say, oh, I'm going to take an integral of this because I have an x and a y. So that's where separation of variables comes in. Okay. Now, if you are asked to do an integral of something, but the only variable in it is the dependent variable, so like this one, the y is the dependent variable, and that's what's in my equation, I'm also going to have to use separation of variables because this is talking about a rate of change in terms of x. Okay, it's how is y changing with x. We need the y over here with the dy to be able to do this. So, so separation of variables, anytime you have multiple variables or it's the y that you have in your equation instead of the x. Okay, if this was just an x minus 1, we could integrate this thing no problem. But if it's a dependent variable, that's when I have to do separation. Okay, so let's take a look at number 5. I've got double variables, right? I've got a p and an m. I'm trying to get an antiderivative of this thing. By the way, I'm going to probably write up into this space too, so if you want separate paper to write that on or something, you're welcome to. But my first mission is to get the m on this side with the dm, and I get the dp over here with the 3p squared. So I'm essentially going to cross multiply. So I'm going to make this square root of m times dm equals 3p squared times dp. And I did that so that now I can come in and say, hey, I want to take an integral on this side and I want to take an integral on this side. I want you to remember that this square root of m is really m to the 1/2 power. So when I go to take my integral or when I go to take my antiderivative, I'm adding 1 to this exponent, which is going to give me m to the 3/2 power. And then I'm dividing by that 3/2, or you can think about it as multiplying by a reciprocal. So this is going to give me a 2/3. And I think we were pretty good at that by the time we finished the last unit. Add 1 to the exponent, and then multiply by the reciprocal or divide. With this one, I'm going to add 1 to that exponent, so this is going to become a p cubed. But then I'm going to divide by that new exponent of 3, and 3 divided by 3 is just 1. So this is really just a 1p cubed, and then I'm going to tack on a plus c. Okay? Now, my general equation means I don't care at all about that c. Okay? I don't have enough information to solve for it. It would vary depending on which type of equation I was working with or what initial value I was given, and I'm not given anything. So I'm just going to leave that a c. And even in situations where you would normally like adjust that c value, like in a second I'm going to solve this thing and I'm going to probably multiply by 3/2, and I would say, oh, I have to distribute it and multiply by it here. That's just giving you a new constant. So you could kind of think about it as like, if we call this c1 and I come in and multiply by the 3/2, that's now a new value of c. Maybe it's c2, and then I'm going to do something else to it, and that gives me c3 or c4. But at the end of the day, it's still just a c value. Okay? And so when you're doing general solutions, and I want to make it super clear that this is only when we're doing general solutions, I don't care about the c. The c is just going to hang out there eternally. Okay? So now my goal is to solve for m. I need m by itself. So I'm, like I was just saying, I'm probably going to start by multiplying by 3/2. Okay, and I'm going to take all of this and multiply by 3/2. And I'm going to be a little bit lazy here. And I'm just going to say m to the power of 3/2 is equal to 3/2 and then this will be p cubed plus c. Now, should I distribute it? Sure. Do I need to? Not really. And I could just put it in front of the p cubed and then again just say, hey, the c is just kind of changing behind the scenes. And that's okay. And then I'm going to raise this to a power of 2/3 to get rid of it, which means all of this is getting raised to the 2/3 power. So I would probably write my final answer here as m equals 3/2 p cubed plus c. Again, I ditched the parentheses because I don't really care about distributing that 3/2. It's not wrong if you left the parentheses in there, and then this would be to the power of 2/3. That's my general solution. Okay? If you did distribute the 3/2 and called this 3/2c, that's fine. If you maybe wrote this as a cube root of something being squared, so we could have also said this is a cube root of 3/2 p cubed plus c, and then this is being squared. That's fine too. Okay. Oh, this is an equal sign in between here because a cube root is the same thing as a power of 1/3. Just recognize that, if this were a multiple choice question, your answer could show up lots of different ways, and you just have to sort of use algebra to know what's equivalent. But again, I don't care about the c. Okay, the c, you can do stuff to it, you cannot do stuff to it. In a general solution, we just kind of lump it all together and call it a c. Okay, that changes when we get down to these ones down below. So let's maybe do what looks hard, number 8 maybe. Actually, maybe I'll start with an easier one. Maybe I'll start with number 6. Yeah, let's start with 6, and then I'll maybe do 8. Okay, I'm going to start the exact same way. So I need a general solution before I can get a particular solution. So I'm going to start by moving the y to the other side. So I'm going to divide by y, which means I'm putting a 1/y here. And then I'm going to move the dx to the other side. My notation's a little wonky there. So I'm going to have 1/y dy equals, and now my y is gone, so I'm going to have 2x dx. Okay? And my mission in doing that is to be able to take an integral on each side. So, integral of 1/y is natural log of y. Integral of 2x is x squared, and this side gets the plus c. Now, normally this is where I would say, okay, just leave that c alone and let's start solving, okay? But this time I have an initial condition. I have this value right here, f of 1 equals 1, which is telling me that when x is 1, y is 1. And so I need to figure out what c value makes that true. So I am putting a 1 here and I am putting a 1 here. So now I have natural log of 1. And by the way, if that were a negative, these absolute value brackets would tell you to make it positive, equals 1 squared plus c. Well, natural log of 1 is 0. So then I have 1 plus c, and then subtract 1, I get negative 1 for my c value. So that was like a little detour, right, where we solved for what c was. Now I'm going to start back over right here with this equation, okay, but I'm going to put the negative 1 in there for c. So I'm taking the negative 1, I'm putting it in up here, and then I'm going to rewrite. So natural log of y is equal to x squared minus 1 now. And now to get y by itself, I'm going to remember that there's an e in the base here. I'm going to spin this thing around, and I'm going to make it y equals e to the power of x squared minus 1. And that is my particular solution. Okay? So what does that mean, that that's my particular solution? Well, it means that if I were to graph this equation, I could express the derivative as this thing, 2xy, if I set this initial condition. It also means that if I were to plug 1 and 1 in, if I were to plug 1 in for x, I should get 1 out for y. And so if I did 1 squared minus 1, I'd get 0 up here, and e to the power of 0 does equal 1. So this is the version of the general solution that fits this particular point. Okay? Okay, let's do one of those that's a little bit harder. Let's do number 8 down here. I think number 8 was an ugly one. Yes. Okay. Separation of variables, but on this one, notice that the y's are on top with this y, so I can't I guess that's what I'm going to do, but I can't just multiply by the y minus 1 over here. I have to divide. I have to divide by y minus 1, so I'm going to end up with this 1 over y minus 1. Oh, and with the dy, I always forget the dy on the left. And over here, what I'd be left with now, because I got rid of the y1, I moved it over here, I would have a 1 over x squared dx. And now I'm going to integrate. These two things look very much alike, but they're going to integrate very differently. This is a natural log situation because it's just a y. It's not a y squared, it's not a y cubed, it's just a y. It does have a minus 1 on there. Because that derivative would still just be a 1, it doesn't matter. So I'm going to now say that this is natural log of y minus 1 is equal to, now let's integrate this side. Now this is really the same thing as x to the negative 2 power. So I'm going to use my power rule. I'm going to add 1 to this exponent, and I'm going to get x to the negative 1. And then I'm dividing by that negative 1, which means I'm just going to get a negative 1 in front. So I get a negative, and this, by the way, a negative exponent means my x is going to be in the denominator, 1 over x plus c. Okay, let's take our little detour and find what our c value is. So I am putting a 2 in for x, and I am putting a 0 in for y. So I end up with natural log of, this is where absolute value is super important, 0 minus 1 equals negative 1/2 plus c. Well, this is really just natural log of 1, which is a 0, equals negative 1/2 plus c. And then add the 1/2 to the other side. So 1/2 is c. Let's start back over with this equation. But I'm going to put the 1/2 in here for c. So I'm going to say natural log of y minus 1 equals negative 1 over x plus 1/2. I'm going to take my base of e and spin this around. So I'm going to say y equals e to the power of all of this, negative 1 over x plus 1 over 2. And then, oh, I missed something, sorry. This y is not just a y, it's a y minus 1. Okay, so I did e to this power equals y minus 1. And now add the 1 over, I think that's what I was thinking of. So e to the negative 1 over x plus 1 over 2. And then with the plus 1 that came from the y minus 1 a second ago. So that's what it means to separate variables and find particular solutions. Okay, particular solution, again, is just doing this middle piece where you're solving for what c is equal to, and then putting that back in your function before you finish it out. Okay, one more big skill would be the exponential functions, so my next video will be covering those.